Okay, this is the start of the recording for Wednesday. Wednesday? Let's see. Wednesday, April 29th. Oh, first section. I uh, accidentally caught myself, but I almost said February 29th, and it's there was a February 29th. This is a leap year, but it's definitely not February right now. It's like almost it's almost not April. Okay, there we go. Words. All right. I still have a little time. Okay, let's take a moment to look at these warm-ups first. I've got indefinite integral of 2x dx, and then the definite integral of 2x dx from x starting at 4 and x ending at 10. So these questions are related somewhat. So I wanted to fit this all on the slide. You'll see why in a moment. But there's the indefinite integral, part one. There's the definite integral. Same function. It's just, is there a 4 and 10 written on the integral sign or not? So part one, just the thing to keep in mind here is that in indefinite integral, these are different creatures, right? Like these just have seem so different. Today's class is trying to like figure out what is the connection between these things because the thought process are totally different. In indefinite integral, the final answer to an indefinite integral problem like this has been a function, or rather, technically a family of functions. Family of, don't worry about this too much, but that's what the plus c part is about. It's like there's actually many functions, but specifically what you're getting is an antiderivative. So for instance, for this one, and you don't even have to take this in the stages, but I'll just go ahead and do it. Like if you move the 2 that's here in front, I'll copy the 2 first, then you have to anti-differentiate x to the first, so you'll have x to the 2 over 2. The 2's cancel. Oh yeah, with a plus c. The 2's cancel, and so you'd be left with x squared plus c. If you don't want to do it quite this way, you could have directly just answered, looking at this up here, you could have just chosen to answer the question by asking the derivative. I mean, it's an antiderivative problem, so the derivative of what thing is 2x, right? And the response to what that is would be x squared plus any number of your choice. X squared plus 2, x squared plus 28, x squared plus 300. Okay, so that's this. Okay, so yeah, and so that could have been done directly, right? Of like, what should you differentiate to get 2x without even this middle step of bringing the 2 out in front? It would have been, you could do this middle circled step if you want, but in the end, it's just, because the number 2 in front is so nice, you might have just gone, oh yeah, I remember that the derivative of x squared is 2x. And then we just put this plus c there. Okay, so that's the indefinite integral. The definite integral, this other one, part two, it's an area, or more specifically a signed area. The final answer is a number, which is it's going to be an area, not a function with a plus c on it. So it's shown in yellow in this picture here. So I graphed y equals 2x, right? That's just a line, slope 2, y-intercept 0. So I just drew that line. Drew in the x values of 4 and 10. Like in some earlier pictures, they have been solid, but I drew them in dotted. I think it'll be easier to spot some of the things I want to talk about. I even put in these x values of 8 and 10, 8 and 20, so that we can compute the area. There's two ways to do it. So here are both ways. One of the ways, and these are both correct. It's not that I prefer one over the other, but one of the ways is going to connect to what we do today. So one of the ways is to take this yellow region and to split it right here so that you have a triangle above and a rectangle below. And if you work it out, I'll skip those details right now, but that triangle has a width of 6 and a height of 12. The red rectangle below has a width of 6 and a height of 8. So all in all, when you do the arithmetic, you'll get the number 84. as the area of the region shown in yellow. Okay, so that's the blue triangle. I'm trying to use color coding here. The blue triangle, and then the red rectangle underneath. That's one way to get the yellow region. 84 square units. Here's another way. Another way to get this is actually a bigger triangle minus a smaller triangle. So sorry, I sort of screwed up the color reveal here. So I'll fix that when I repost the slides. But you could think of the yellow region again that we want is think of it like there's this huge triangle out here first that I asked for purple, and this is what the computer gave me for purple. Sorry. So 10 times a width of 10 and a height of 20, and it's a 1/2 base times height. But that big triangle is too much. It's more than the yellow region. We have to subtract off this region that I just shaded in green. We need to subtract off 1/2 times base of 4 times height of 8. Okay, and you could leave your work like this, as far like this or like that, as far as I care. I just want to illustrate that we're going to get the same number. So let's just go through this. 10 times 20, 200. 4 times 8 is the 32 here. What's 1/2 of 200? That's 100, right? Half of 32 is 16. And if you do 100 minus 16, you get 84. Same answer either way. But the point, so we've done actually part 2, this question, 2 different ways. But in both cases, by interpreting it as what's the yellow area, you end up with the number 84, either as the area of a triangle above plus the red rectangle below, or as a huge triangle that has too much, and so you have to subtract off the area of this small green triangle. Either way, you get the number 84. Okay, so I hope what this warm-up does is it helps with the whole, like, this problem turned into this antiderivative thing, and this problem turned into a number, and we did it 2 different ways. What I want you to do for the next slide is copy down, please, if you haven't been taking notes, with at least this much. Antiderivative, or integral, indefinite integral of 2x dx equals x squared plus c. Get that. And then get the part 2 question. So integral 4 to 10 of 2x dx. And write that that is equal to this one. I bolded this so that I would remember to talk about it. So equals 100 minus 16. So if you'll write those 2 things for a moment. Again, it's integral of, it's this equals that, and then write down this equals that. We're going to use those in just a moment. That's why. And as long as you're writing, anybody have questions about the warm-up? Okay, so far, these 2 questions, the notation looks so similar, but yeah, right? So there's a question and its final answer. Here's a question, and without showing all of the work we did earlier, the final, not even a final answer, but an answer, close to a final answer. These have looked so different, and the complaint maybe that you've had is like, how come the question here and the question here, how come they look so similar? Like, it seems just mean to have notation that looks this similar and our thought process are completely different. And to start seeing the connection between these, I'm going to suggest we rewrite this ever so slightly. So I copied this left side, integral of 2x dx from 4 to 10, from x is 4 to x is 10, but I rewrote 100 as 10 squared and rewrote the 16 after the minus sign as a 4 squared. Now check this out. You see the connection a little bit more, maybe with this x squared here and this 10 squared and 4 squared. I'll just really point it out and do some highlighting. 10 squared is what x squared is once you plug in 10 for the x. And then 4 squared is what x squared is when you plug in 4 for the x. Right? So plug in this 10 in for x squared there, and then plug in the 4 in for x squared. So there seems to actually be a connection here. It seems so strange, but it works out every time. We're not going to prove this theorem, but what you're actually seeing here is an example. Up here is an example of this theorem. So I would write this theorem down. Let me read it aloud. The fundamental theorem of calculus. It's the most important theorem in calculus with a name like this. If little f is a continuous function on the closed interval from a to b, and capital F is any antiderivative of little f, then the definite integral from little a to little b of little f of x dx equals capital F of b minus capital F of a. Let me make sure everybody has a moment to write. Okay, I know that these sorts of things, when we look at them first, are so confusing and abstract. This is a continuous function part. I wouldn't stress about it too much here. Um, yeah, it's the functions we'll be looking at doing this too will be continuous functions. I just needed that for the technicality of it. Here it says capital F is any antiderivative of little f. And even here you might be like, wait, I thought you promised there'd be both of these in the box, and they're both here. So this, first of all, the definite integral, that's here it is generically. Here's a specific one, right? So in generic, it's just little a and little b. Here specifically, it's 4 and 10. Generically, it's a little f of x. It's the function 2x. Where's the capital F, you say? I mean, capital F is an antiderivative, and that's what this was, remember? So it's in words. Antiderivative, that's what the indefinite integral problem was about. So that it does actually appear, right? The indefinite integral appears just in words. You're supposed to use any antiderivative you want, and as an antiderivative, it's x squared plus a number. So what's an antiderivative? X squared plus 2. Another antiderivative of x squared plus 3, x squared plus 4, x squared plus 5. These are all antiderivatives, but the most convenient antiderivative is if we just use x squared plus 0. So that's the antiderivative I'd like to use. That's my capital F. Capital F of x is equal to x squared plus 0. And that's what you'll notice is, so capital F of b. So if this is your capital F right there, then b is this number. That's the 10 in our example. So it's plugging 10 into x squared. That's exactly what we said right here. So I'm just saying all this to say, if you're looking for an example of this process, we've technically already done it here, but it's sort of all backwards because we were doing this stuff and I was kind of leading you on and using this as a discovery process to see that this thing happen, and we will see more examples of this in just a moment. Before looking at the examples though, just a couple things to talk about. It really is capital F of b minus capital F of a, not the other way around. Common error is people write capital F of a minus capital F of b, I think because they're thinking alphabetical order or something like this, but we saw in our own example that it has to be capital F of b minus capital F of a. We had 100 minus 16, not 16 minus 100. Why? Because that's just how it worked out in the warm-up. So please be careful about that. Don't accidentally swap these. It's got to be capital F. It's got to be, take your antiderivative, plug in the upper number of the integral first, and then the lower number after. That's just how it is. For notation's sake, another way to write capital F of b minus capital F of a, if you'd like to, is to write just your function first, so your antiderivative function, capital F of x, and this vertical pipe, and then a b above and an a below. It's just notation, okay? And like anything, else, just with notation, we just got to get used to it. So I won't use it right away on like the first example or two, but you'll see me start to use this so that you can get used to it. And if you don't like the notation, you don't ever have to write it yourself. You can always write it this way. I just want to show you your options. Just so that we can already start practicing this notation though, let's continue it with this example. So if, for instance, you had capital F, and I'm picking an antiderivative, was x squared. So here's all your antiderivative, x squared plus 2, x squared plus 12, x squared plus 38. But if you plug in c as 0, that's a specific antiderivative. It says any antiderivative, so I'm using capital F of x equals x squared. Then this notation, if you write capital F of x, vertical bar 10 above, 4 below, that's, as this is explaining here, it's notation for capital F. I'll just replace the capital F with x squared first. So x squared, vertical bar, 10, 4. And then this, explained here, is take your function, plug in the upper number first, the b, in this case 10, then plug in the lower number 4 next. Okay, that's a lot of talk on this. I think what's going to help us out is if we start looking at a new example. Okay, so we're gonna do this thing, right? We're gonna get this definite integral problem. We're gonna find an antiderivative of the function that's mentioned right there, and then we're gonna find the value of that new function capital F at two specific x values and subtract. So here's the problem: integral 4 to 10 3x squared dx. So not that you have to point out these pieces all the time every time, but I want to connect what's generically inside that theorem box to the specifics of this problem. So the function that appears inside the integral, it was called little f. Little f of x is 3x squared. The x values are 4 and 10. Right, so the first x value was called a generically. In our problem, a is 4. So as an answer, what we're going to do is look at the indefinite integral first. The key warning I want to say is please don't say that this is equal to that. This is a definite integral, this is an indefinite integral. Those are never equal. So if we look at this indefinite integral, that is, find an antiderivative, we'll get x cubed plus c. Now, remember this plus c means you pick any number you want to get an antiderivative. So x cubed plus 2, x cubed plus 8, x cubed plus 35, x cubed plus a million. These are all antiderivatives. And here's one specific antiderivative. I just plugged in c is 0. So capital F of x equals x cubed alone. That's an antiderivative. And the fundamental theorem of calculus said pick an antiderivative of your choice. So this is an antiderivative of 3x squared. And then what you do is go back to your original problem, and you just, based on what your capital F is, you plug in 10 for x, the upper number here, into the antiderivative, and then you plug in the lower number here in for x into that same antiderivative. So in this problem, now we have an algebra thing, right? So capital F of 10, that's 10 cubed, minus capital F of 4, that's 4 cubed. Now I do want to simplify this to make a point. I mean, I would say, when it comes to the final exam, I would just leave it like that, 10 cubed minus 4 cubed. But because of the point I want to make, let's just simplify. This is 1,000 minus 64, which ends up being 936. I also want to dig into what it means by in the fundamental theorem of calculus. It says you can use an antiderivative of of little f, and any antiderivative you want could be capital F. So here's a different way to answer this same question over here. Second answer, first of all, I wanted to start the same, so there's that same indefinite integral, and then you can pick x cubed plus, you pick any fixed number you want for c to create an antiderivative. So I just picked 1, 2, 3, 4, 5. Just why not? So in the first answer, this is probably the preferred answer. I wouldn't even write all this down right now, right? So the thing is, in my preferred answer, my capital F is just x cubed plus 0. But you could use for capital F x cubed plus 1, 2, 3, 4, 5 if you want. It's just a little more writing. So then what happens? Well, just like here, this part looks the same. It's just now capital F is this function instead of that function. So you plug in 10 for x here, then you plug in 4 for x here. You are going to need parentheses this time around because after the minus sign, f of 4, it's two terms, so it's got to be in parentheses. If you distribute this minus, well, you have a plus 1, 2, 3, 4, 5 and a minus 1, 2, 3, 4, 5. They cancel each other out to a 0 anyway, so you're still left with 10 cubed minus 4 cubed, which is still 936 anyway. So it's just, this one works technically. The second answer works. It's just more writing because of needing to write 1, 2, 3, 4, 5 these extra times. So it's not worth it, really. It's just, I'm just pointing it out because you can do it. It's just the most convenient antiderivative to use to make your capital F. You have a choice of what your capital F is, but it's nice to stare at this and plug in c as 0. So technically, I probably should have written a plus 0, but I was too lazy to even do that. Right? So I would just, when it's the indefinite integral, this requires the plus c here. You got to write that there in the indefinite integral. But when it comes to a specific antiderivative, just plug in c as, since you get to plug in any number you want, why not plug in c as 0? So you don't have to even write plus 0. Okay, let's pause, make sure we're doing okay overall. That overall the process was look at this function, find an antiderivative. We're stating all the antiderivatives this way. Here's how we're stating a specific antiderivative, and then we're plugging in to this antiderivative x cubed. We're plugging in 10 and we're plugging in 4. That's what happened here, and that number simplifies down to 936. I will ask and suggest that well, it's good to take notes anyway, but please at minimum write down this, the original question up here became 936. So if you would, I'm going to give you a moment to make sure that at least that's written down. Let's see if there's any questions that pop up from anybody while that happens. So definite integral 4 to 10, 3x squared dx equals 936. That's what I have at the beginning of the next slide, in fact. So the work that we have here, integral 4 to 10, 3x squared dx equals 936. So we are actually going to use this fact in class next time. By next time I mean, well, tomorrow's exam. So I mean on Monday, I will bring this fact up again to address a certain kind of error that sometimes people make. So put a star by this. We're going to use this next time. We will literally use this fact next time. Here's the funny thing. This number that we got is a whole number, right? It's not a decimal. It's a whole number. To me, this is surprising since the picture has a non-straight side. Let me pull up a picture of this. So if you click on this link, I've got it already here in another window. I just need to slide this over here. Take a look. So this is okay. Look, the problem is it's a definite integral, meaning this is an area problem still, right? So there's the function 3x squared shown in red, and the two vertical lines x equals 4, x equals 10. Those are the numbers on the top and bottom of the integral sign, and the space, the region that is under the curve, under the function, but above the x-axis and between the two vertical lines is shown here in blue. This region has 4 sides. There's this vertical line that's a straight side. This other vertical line is a straight side. At the bottom, the x-axis, that's another straight side. But there's a 4th side, and it's not straight. It's made out of a parabola, right? Like you can see it's kind of much curvier here. This part, you might be tricked into thinking that it's straight, but it's not, right? So sometimes the way that people try to do this definite integral problem, they'll say, oh yeah, this is an area, so I'm going to cut, right where this 448 is, I'll just draw a line across, and then I'll have a rectangle below, which is true, and I'll have a triangle above, which is not true. There's not a triangle above. It looks like a triangle, but this red side is not straight, even if it sort of looks straight. It's curvy, right? So I point this out to say that I appreciate the thought of trying to find the answer to this question by doing like the area of a triangle plus the area of a rectangle, but there's not a triangle here. But the key thing is this is an area. That's the strange thing about what we just did. The most surprising thing is even though there's a curve, even though there's this curvy side, this top side is not straight. It's part of a parabola. The exact area, I mean literally the exact area of what's shown in blue. I didn't expect it to be a whole number, but it is. It's literally exactly 936 square units. Folks, we found an area without using traditional area formulas. We didn't do like a 1/2 base times height because there's no triangle, we can't. And we didn't, do like length times width for a rectangle, and that's the way we found areas in the past. We didn't use any of those area formulas, but we found an area. We found an area of a thing that has a curvy side to it. An exact number, 936. So let's do another example. Integral 3 to 9, 2 over x dx. Okay, so first, let's look at an indefinite integral. Okay, let me point out in red, this is sometimes what people do. They'll take the original question up here and say that it is equal to, and then just leave off the 3 and the 9. This is the next step, but they're not equal, right? So and this is a definite integral. This is an indefinite integral. Please don't ever say that a definite integral and an indefinite integral are equal, because one of them is a number, right? Definite integral is going to be a number, and an indefinite integral is a function plus c. So just write instead just, this is the next step, but just write it on its own line. On its own line so that you have no temptation of writing an equal sign next to the thing. So integral 2 over x dx on its own line. So here it is. I have this on its own line, integral 2 over x dx. And this ends up being, well, you can bring the 2 in front if you want. So do that. Then you need to integrate 1 over x, which is going to be ln of absolute value of x plus c. So shown here are all the antiderivatives in a sense, right? If you plug in c as 1, or plug in c as 2, or plug in c. Here's some examples. Plugging in c as 0, you have 2 ln of absolute value of x. Plugging in c as 1, you have 2 ln of absolute value of x plus 1. Plugging in c as 3, 2, 1. These are all antiderivatives. And not that you would point this out, when you're working on something like for the final exam or anything, but like I'm pointing this out for the purpose of class discussion to say that the most convenient antiderivative is this one when you plug in c as 0. So I would just use, when writing the antiderivative, you do need a plus c here to write this indefinite integral problem. But when it comes to picking a specific antiderivative, the most convenient one is the one that requires the least writing. Capital F of x equals 2 times ln of absolute value of x. We've plugged in 0 for the c. And now then we can go back to the original question, and we'll use this specific antiderivative. There's the original question. I'm just getting you used to the new notation a little bit, so it's this capital F. And we're going to plug in 9 for x first, and then 3 for x next, with a minus sign. So this really just notation translates into f of 9 minus f of 3. So if you want to skip writing this and you just go directly to here, that's fine. I just want to show what the notation looks like. But then f of 9 is 2 times ln of absolute value of 9 minus, and then f of 3 is 2 times ln of absolute value of 3. This is the place I'd leave your answer as far as, work on paper goes. And this is the exact area, but just to discuss things, I did type this into a calculator. You get approximately 2.1972. And so in the picture here, if you click that link, 2 over x, I've got this 2 over x, that's in red. So between that, the x-axis, and then these x values of 3 and 9, this blue shaded region here, it's 2.1972 units, approximately. That's really close. Like the actual number of units is literally 2 ln of absolute value of 9 minus 2 ln absolute value of 3. So let's just pause here for a moment and see if we're okay. Do you want to see the next example? Are there any things I can say about the process we did for this one? Okay, let's do another one. Oh wait, question just came in. When figuring out definite integrals, do we always use this process, or the one we did yesterday with the drawings? That's a good question. I really appreciate that question. And this is you do you. This is like you do whichever way you want to, as long as the process works. So some of these problems you can do both ways. So the before today method of drawing a picture and finding an area, if you you can do it that way, then do it that way. But you notice like this last one we looked at has this red curve. Drawing a picture and then trying to get the area is not going to work, right, for this one. So that method doesn't always work. The method we're using here, the fundamental theorem of calculus, like shown here, this method also doesn't always work. So there are problems where both methods work. There are problems where only one method works. So you got to just, whichever way works. I'm not going to ever say you have to do it this way or that way, unless, of course, there's only one way to legitimately do it. The other question that came in was, do we have to put units? No, you don't. You can just say, you just leave it like this, in fact. I'm not expecting anybody to if you do the problem this way, I'm not expecting people to, first of all, I would just end it right here, right? And then to say number of square units, you don't have to. If you want to say, write square units here, fine. I'm just trying to really emphasize that even though we didn't think about it much like an area, what we actually computed really is an area. I'm just trying to emphasize that what happened is the computation of area without using any traditional area formulas like the area formula for a circle. That's all. So I'm not expecting people to put units, but I just keep putting them here to emphasize that these are areas. That's all. I hope that addresses both of the questions. And Marissa, this issue you're talking about, like, do we always use this versus the other? There'll be a little summary at the end that helps, I hope, clarify that a bit as well. So let's do another one as a whole group here. Definite integral 2 to 10, 3 to the x dx. We should look at an indefinite integral first. And here's another version of an error. It's actually like, to me, this is somehow the same error as in the past. So people will take the original question and they'll write 3 to the x over ln of 3 plus c. The problem here is that this left side is a definite integral, and this would be the result of the indefinite integral. So this, if we looked at the antiderivative of 3 to the x, I'd be expecting a 3 to the x over ln of 3 plus c. So this is still setting equal a definite integral and an indefinite integral. Even if it looks a little different than the last time, this morally it's the same. Don't set a definite integral and the result of an indefinite integral equal. Instead, just get that on its own line. So there's the problem. Get the indefinite integral, so without the 2 and the 10, on its own line and just write this antiderivative. So this is a standard antiderivative rule for exponential functions. Now that we have, this is a statement of all the antiderivatives, but the most convenient one is when you plug in c is 0, right? So looking at the original question, here what I've done is I've taken the specific antiderivative. Which antiderivative? The one where you plug in c is 0. So just this circled here is what's showing up right there. That's the antiderivative where you, so circled here is the antiderivative when you plug in c is 0. When stating the indefinite integral, this plus c here is required, but not here. This is, we have chosen a specific antiderivative. And now, with what's written here, we just need to now plug in the 10 for x first, and then the 2 for x next. So 3 to the 10 over ln of 3 minus 3 to the 2 over ln of 3. I ran that. So this is how I would expect a final on paper answer looks, but I ran this through a calculator. I got 53,000. I will also, again, pull up a picture of this. So in the picture, the blue shaded region is 53,740 square units. Right? Now, that's this region here. It's not a triangle, right? There's like this curve, this exponential curve in red. Sorry, it's maybe even hard to see that it's in red. I'll just turn off the blue thing for a moment. Yeah, so there's that under the curve, but above the x-axis. This region here is 53,700 whatever square units, right? That's what we found. This one would have to be done using this method. You couldn't, treat it like a triangle. So does that work? I've got one more example for you, but I just see if we're okay with this. Usually the hang up on this one is, where did this come from? And the reminder is the antiderivative, the indefinite integral for an exponential function. We had discovered this was a formula, like we had like integral b to the x dx was b to the x over ln of b plus c. So we're just applying that formula. Okay, I have another full class example here for you, and I will not point out the same error again. I mean, let's point out a different kind of error and so a little later in the problem. Sometimes the warning too early, it's like, well, let's just get through a problem first. So let's look at this. Integral 1 to 4 of the function 6x minus 5 dx. So straight away, the thing to do is to look at the indefinite integral. And in fact, the way I usually do this is just because there's always that temptation to write an equal sign, I just write like indef, just for myself. You don't have to write that, but like somehow just writing even that little short indef as short for indefinite integral is helpful for me as a reminder to not write an equal sign between this thingy and that thingy. And these are not equal, and so there shouldn't be an equal sign between them. So here's the indefinite integral, and so we have an antiderivative problem. So you anti-differentiate 6x, you get 3x squared. Anti-differentiate 5, you get 5x, and then there's a plus c. So here's a statement of all the antiderivatives. By all the antiderivatives, I mean when you pick a different c, you get a different antiderivative. But the antiderivative I like the most is when you plug in c as 0. In other words, boxed there. That is the antiderivative that I want to use. And so we go back to the original problem at the top, and using this specific antiderivative here, the one where you plug in 0 for c, there's two variables here. There's a capital C, there's a little x. So I want to be clear, if you plug in 0 for c, you get a specific antiderivative. And so that specific antiderivative, namely 3x squared minus 5x, I need to plug in x is 4, and then plug in x is 1. Here's one notation for it. You could, here it is written out, right? So plugging in x is 4, and then plugging in x is 1. I would just leave it like this. Why even bother simplifying further? But just so that we can talk about things, I went ahead and simplified. That number ends up being 30. The warning I want to talk about this time, we haven't. We're done with the problem, but just now to talk about a warning that sometimes comes up is sometimes people take this part and that part and accidentally swap the two. So please don't do that, right? So be sure to plug in the upper number, in this case 4, first, and then plug in 1 next. If you swap, if you accidentally swap the two things in the square brackets, you'll end up with what's shown in red, which is an error. It's a common error. So it's a different kind of error to discuss than we have for the other problems. But I thought, and we already actually mentioned this early on, but just worth mentioning again. So please be careful not to swap these. So the area that we get, the signed area, is actually 30 square units. I would like to show a picture again. So in this picture, the signed area is 30 square units. And look, this region is above the x-axis. It's above the x-axis. And this one we found using the fundamental theorem of calculus just now. Right? We applied this theorem that incorporates using the antiderivative. But in this problem, the blue shape here is actually made of 4 straight lines. So we could have done it the way that we had originally, like yesterday or the day before. We could have, split this up like right here, down the little rectangle at the bottom and then a triangle above, and we could use traditional geometry formulas for area. This one you can do both ways. So I hope that helps address maybe the point, the question that came up. At least it came up privately. Again, to read that question, since everybody didn't have it, the question was, when figuring out definite integrals, do we always use this process? This process meaning the fundamental theorem of calculus method with the antiderivative, or the one we did yesterday with the drawings. So this is an example of a problem where you can do it both ways. Either way is fine. All right. Let's do the following unless there's questions. Couple practice problems. It's not maybe enough time for all of them. There's 18 minutes left in class. I do want to use the last 5 minutes to do a round of announcements and also to help clarify any confusions that might come up related to tomorrow's exam and things like this. So just some time to work on these 4 questions. You let me know if you have any questions. I will, try these out. I would in all cases practice this new thing. Actually, the drawings way I don't think is going to work for any of these. So in each case, do the fundamental theorem of calculus. Try today's new method. Okay, I've got about 6 minutes. I'm not going to completely do question 4, but I'm just going to point out for question 4. Again, don't say equal, just like on its own line, indefinite integral. Well, didn't mean to do that. Indefinite integral, x to the fourth times quantity x plus 8 dx. It's like, how do we do this antiderivative? Well, I would say you first distribute the x to the fourth. So x to the fifth plus 8x to the fourth dx. And then you can anti-differentiate each of the terms separately. X to the 6 over 6 plus 8x to the fifth over 5 plus c. And then this is the antiderivative I'd use and plug in 3 first and then 2 next. So I didn't do the whole thing here. What I actually I just wanted to point out that sometimes, when you do your antiderivative, you won't anti-differentiate right away. Sometimes you got to do a little algebra first. I will post complete solutions, so there is a link that you can click on. The link doesn't go anywhere right now, or rather it goes to like one of those file not found things. I just haven't had time to make a full set of solutions. I'll do that, but it's not relevant for tomorrow's exam anyway, so I'm focused on sort of that sort of stuff. What I want to do here is actually take a moment to say, let's clear up some things about this definite integral, and within this slide you'll see some discussion about things to be careful of even for tomorrow's exam. So first of all, excuse me, when you have a definite integral problem, your final answer is going to be a number. One method is to draw a picture, right? So interpret this as a signed area, draw a picture. In fact, sometimes it's the only way to do it. Sometimes you have to draw a picture. So like a problem that looks like this, at least as far as the ways that we've looked at in this class, this is going to be half of a circle. So this one, after drawing a picture, it's 1/2 times pi r squared, right? So also if within the integral, the function here part has absolute value, that's going to be a v-shape, and we don't have some process to anti-differentiate. If you try the method 2, which we're going to mention in a moment, sometimes people try to anti-differentiate and don't know what to do with the absolute value, so just try to ignore it. But instead, draw a picture for this kind. But the whole point is, when you have this definite integral, so there's yesterday's thing, draw a picture, think of it like an area. But now the new method looks totally different, is just momentarily look at the indefinite integral. The point being that you have this, you do your anti-differentiation, and you have this plus c, but then take a specific antiderivative, usually the one where you plug in c is 0, and then you apply the fundamental theorem of calculus. The key thing I want to talk about, so none of this stuff is for exam 4, but talking about finding this antiderivative, how do you do that? How do you compute an indefinite integral? Here are some comments that are relevant for exam 4. Right? So sometimes what you need to do are these integral methods, or these antiderivative methods that were prior to when we learned substitution. So for instance, undoing the power rule, you raise the exponent up by 1 and divide by the new exponent. Oh yeah, with a plus c, right? Or one time, when the exponent is a -1, you have ln of absolute value of x plus c. Here's the one for exponential functions that often people forget. So here are the sort of main antiderivative rules or indefinite integral rules we learned of before doing substitution. Sometimes, instead of sometimes you have to rewrite the antiderivative problem by doing a little algebra first. That was why I wanted to even preview that last example there, where we had to distribute that x to the fourth. Okay, so sometimes you got to do that first before looking at your antiderivative, and then sometimes you have to do substitution. You do use substitution. This is not always. This is not my go-to. In fact, it's time-consuming. If it works, great, but like sometimes you have to just do a little algebra instead of doing use substitution. So these triangular bullets here, these are the things to keep in mind. These are the things to think about as far as exam 4 has antiderivative problems. It doesn't have this stuff. It has no signed area stuff. It doesn't even have fundamental theorem of calculus. It's just the mini part here where you do antiderivative. And these are the things I want you to keep in mind, that there are different methods. And so if one of your methods isn't working out, try another. Again, just to emphasize here, exam 4 does not have definite integrals at all. It does have indefinite integrals. So it has, these 3 techniques are relevant for exam 4. Just comments, right? So announcements. Today is the day before the official date of an exam, so please do the math as a process pre-exam assignment. Because tomorrow is the date of an exam, there's no live class tomorrow. I don't want to shove extra content. That's not the whole idea here. I want to take a day off from being in class. You have a 5 hour window of, pick your own 5 hour window of time between Thursday and Friday to work on it. And the format difference is turn in a single file, one PDF. So just there's some instructions about that. If you are stuck, just certainly send an email. And with that, I think we will. Please, if you can, look at WebWork 41 today. And with that, I will say let's end class.